what if I told you that teaching a small everyday AI to just perfectly copy the answers of a massive genius level AI, that it actually makes the small AI worse at its job?
Right, which sounds completely counterintuitive. I mean, you'd think that copying the smartest kid in the room is just a guaranteed A+.
Exactly. But, like, in the world of large language models, copying the right answer without seeing I guess, the messy internal scratch pad used to get that answer, it's a recipe for
It
disaster.
really is.
And right now, the absolute smartest AI models on the planet, things like GPT-4, they are essentially locked inside these high-tech, impenetrable vaults.
Yeah, total black boxes.
Right. There's an absolute genius sitting inside that vault, but you cannot see its scratch pad. You can basically only slide a piece of paper under the door with a question on it, and then just wait for it to slide a perfectly typed final answer back out.
Which is, frankly, the defining bottleneck of the modern AI landscape for anyone listening who wants to actually build things.
Oh, 100%.
We have these proprietary mega models that are incredibly capable, but they're completely locked behind corporate APIs.
Yep.
They're expensive, they require massive data centers to run, and like you said, they operate as pure black boxes. You have zero access to their internal wiring or their step-by-step reasoning.
And that is incredibly frustrating if you're a developer or a researcher or just, an enthusiast who wants that level of genius running locally, like for free on your own hardware.
Exactly. You want to actually own the model.
Well, today we are unpacking a brand new technique that might finally let us do exactly that. Welcome to today's deep dive. We're looking at a fascinating research paper from Yat-sen University and Alibaba, and it's titled Knowledge Distillation of Black Box Large Language Models.
It's a great paper.
It really is. So the mission for our deep dive today is to explore a structural breakthrough they call Proxy-KD, which basically acts as a bridge between those closed-off mega models and the smaller open source ones you could actually run on like a laptop.
So to appreciate how this Proxy-KD method breaks that vault wide open, we first have to kind of ground ourselves in the mechanics of how AI models normally learn from each other.
Right. Set the stage for us.
So the core concept here is called knowledge distillation, or KD. And the goal is to train a small, highly efficient student AI by having it learn from a much larger, smarter teacher AI.
Makes sense.
You are trying to compress the vast, nuanced knowledge of a giant model into a much smaller architecture. To give you a sense of scale, a teacher model might have over 1 trillion parameters.
Wow.
Which requires millions of dollars in server racks just to run. While a student model might only have, say, 7 billion parameters, which you could easily run locally on a standard MacBook.
So it's extreme compression. But, to understand how this new paper achieves that compression, we kind of need to understand why the current teaching methods are falling short, right?
Yeah, exactly.
It seems to come down to a core conflict in the research, which is the paradox of the black box versus the white box.
Right. Historically, knowledge distillation falls into two main camps, based entirely on how much access you have to that teacher model.
Okay.
Let's start with the ideal scenario, which is white box knowledge distillation. In a white box setup, the vault door is wide open. You have total access to the teacher model's internal brain.
So you can see everything.
Everything. You can see its hidden states, its attention scores, and most importantly, you can see the probability distribution of every single word it considers before it speaks.
Okay, let me make sure I'm visualizing this probability distribution thing correctly. When a language model generates a sentence, it doesn't just confidently pick one word and move on, right?
No, not at all.
If I give it the prompt, the cat sat on the model evaluates a whole spectrum of options simultaneously.
Right, it's calculating the odds.
So it might calculate internally, I'm 90% sure the next word is mat, 9% sure it's floor, and 1% sure it's dog.
Yes, and that underlying math is the golden ticket. We call those probabilities soft labels.
Soft labels, okay.
And they are incredibly rich in information because they teach the student model the nuance of the language, not just the final vocabulary word.
Got it.
To actually transfer that knowledge, researchers use a mathematical function called Kullback-Leibler divergence, or KL divergence.
Okay, KL divergence. I've definitely seen that term thrown around in research papers, but how does it actually work in practice?
Think of KL divergence as a highly sensitive distance tracker. It mathematically measures the gap, or the distance, between the student's probability guesses and the teacher's probability guesses.
Oh, I see.
So if the teacher thinks the word mat is a 90% probability, but the student only gives it a 40% probability, the KL divergence calculates that massive gap.
And then what does it do with that gap?
The training algorithm then uses that measurement to literally physically tweak the internal weights and neural pathways of the student model. It forces its internal probability curve to bend and stretch until it perfectly overlaps with the teacher's curve.
Wow.
Yeah, it's basically forcing the student to adopt the exact same thought process.
So Whitebox-KD is like having a tutor sit down with you and show you their entire step-by-step scratch pad, explaining their whole thought process.
Exactly.
That sounds perfect, but I'm guessing the catch is that the models where we actually have this wide open white box access are usually open source models, which means they just aren't as smart or capable as the giant proprietary ones.
Right, bit the rub.
So it's like the tutor is showing you all their work, but the tutor only has a C+ average in the subject.
That is a perfect analogy. The capacity of the open source teacher is inherently limited. Now, flip that around to the other side. Black box KD.
Okay.
This is where you use a proprietary genius like GPT-4 as the teacher. The intellect is brilliant, but because it's a closed black box, you get zero soft labels.
None at all.
None. You don't get the probabilities, you don't get the scratch pad, and there is no KL divergence to track the distance between their thought processes. You only get the final output, what we call hard labels. You just get the word Matt.
So it's copying the smart kid's answers without the scratch pad. Wait, if copying the final answer works for that one specific test, why does it fail when the model gets out into the real world?
Well, because of brittleness. I mean, rote memorization doesn't teach the underlying logic of how to solve a problem.
Right.
If the student model just memorizes that Matt follows cat sat on the next time it faces a slightly different sentence structure, say a complex logic puzzle about where the cat is located relative to the furniture, it completely fails.
It just doesn't know what to do.
Exactly. It doesn't have the foundational reasoning to adapt to new contexts.
Okay, so the smart models are locked and the open models are limited. It sounds like up until now, we were just stuck choosing between two massive compromises.
We were.
Like, we either get genius-level answers with zero explanation or great, transparent explanations from a mediocre teacher.
Yeah, and until this paper, the field was largely stuck making that exact trade-off. But the researchers hypothesized that if we can't look inside the genius black box to see its work, we just need to build an intermediary that can show us its work.
Which brings us to the core structural innovation of this research, right? The Proxy-KD architecture.
Exactly. So the researchers recognized that having a tiny 7 billion parameter student model learned directly from a massive trillion parameter black box model creates an insurmountable capacity gap.
It's just too big of a leap.
Right. The small model simply lacks the neural real estate to connect the dots between a complex prompt and a genius-level hard label. So they insert a proxy model right in the middle of the training pipeline.
Okay, let me make sure I'm picturing this workflow correctly. Instead of going straight from the teacher to the student, the data flows from the teacher to the proxy and then finally to the student.
Spot on. And the choice of that proxy is the key to the whole operation. The proxy they deploy is a large open-source white box model. In the paper, they primarily use Llama 270B. So that means it has 70 billion parameters. It's massive enough to possess a very strong foundational intellect. It has the raw capacity to handle complex reasoning.
Right.
But crucially, because it's an open source model, the vault is completely open to the researchers. We can see all of its internal math, its probability distributions, and its soft labels.
And then the student model is the small one.
Exactly. On the far end of the pipeline, the final student model is much smaller, like Llama 17B or Llama 27B.
So to carry our analogy forward, the 70B proxy acts like a highly qualified substitute teacher.
I like that, yeah.
It watches the genius professor, GPT-4, and learns to mimic their behavior. Then it turns around and shows the much younger student, the 7 billion parameter model, all of its internal transparent notes.
Yeah.
So we get the big brain of the closed model translated through the complete transparency of the open model.
The dynamic is brilliant on paper, but you can't just grab a 70 billion parameter model off the shelf, drop it in the middle, and assume it's going to flawlessly translate GPT-4's logic.
Oh, you can't.
No. If you do that, it actually creates a catastrophic game of telephone.
Wait, why would the proxy mess it up? Doesn't it just, like, read the teacher's answer and pass it along?
Well, the proxy is a neural network with its own inherent biases, right? Its own default probability distributions, and its own unique way of looking at the world.
Oh, I see.
So if it reads the black box teacher's final answer, but its own internal math guesses a completely different reasoning path to get to that answer, it passes that flawed, hallucinated logic down to the student.
Ah, so it makes up the wrong math for the right answer.
Exactly. So the proxy has to be aggressively trained to abandon its own native instincts and adopt the teacher's instincts. Which brings us to the most critical phase of the researcher's methodology, alignment.
Okay, so how do they actually force this proxy to stop thinking like itself and start thinking like GPT-4?
It starts with a very strategic data split. They compiled about 1 million sequences from data sets like OpenOrca and Nectar.
What are those?
These data sets are essentially vast collections of highly intricate user prompts paired with detailed responses generated by GPT-4.
Okay, got it.
So they take the first 10% of that data and use it to just warm up the proxy using basic supervised fine-tuning. It gets the proxy used to the general format of answering complex questions.
Right.
But then they take the next 45% of the data, nearly 500,000 sequences, and run it through a rigorous process called direct preference optimization, or DPO.
Wait, DPO, direct preference optimization. I know I've heard of this. Isn't that the tool companies like OpenAI and Anthropic use to make their chatbots polite and helpful?
Yes, that's right.
Like stopping them from generating toxic content or giving dangerous instructions? How does making a model polite help it clone GPT-4's math and reasoning skills?
That is a very common misconception, actually. DPO is frequently used as a politeness or safety filter, but at its core, it is simply a fundamental alignment algorithm.
Oh, okay.
It is a mathematical lever for changing a model's default behavior. Here's how they use it, not for safety, but for cloning logic.
Walk me through it.
You take a complex prompt, and you feed it to both the black box teacher and the proxy. The proxy generates its answer based on its own unaligned natural instincts.
Right.
At the same time, you have the teacher's flawless answer. The DPO algorithm looks at both. It then goes deep into the proxy's neural network and mathematically penalizes the specific weights and connections that led to the proxy's flawed instinct.
Wow.
And simultaneously, it reinforces the weights that align with the teacher's answer.
So it's literally physically altering the probability landscape of the proxy's brain.
It is reshaping the terrain entirely. If you imagine a ball rolling down a hill as a thought process, DPO is building walls and digging trenches so that the proxy's ball always rolls down the exact same path that GPT-4's ball would roll down.
That's a great visual.
It mathematically forces the proxy's neural pathways to strongly prefer the teacher's output over its own native instincts.
That is wild. It's systematically overriding the proxy's original personality and molding it into a clone.
And the researchers proved how vital this terrain shifting is through extensive ablation studies.
Ablation studies?
Yeah, an ablation study is when researchers intentionally strip away a piece of their system to see if it was actually contributing to the final result.
Okay.
When they skipped this DPO alignment phase entirely and just used a raw, unaligned Llama 270B model as the proxy, the performance of the final student plummeted.
Really? How bad was it?
On a benchmark specifically designed for complex reasoning called BBH, skipping alignment caused a massive 10.40-point drop in the tiny student's final score.
Wow. 10 points is huge.
On math tasks, it dropped by over 5 points. A poorly aligned proxy doesn't just fail to help the student, its confused internal logic actively poisons the student's learning process.
Okay, I have to push back here, though.
Sure.
Because even with DPO, even with 500,000 training examples tweaking its neural pathways, the proxy isn't going to be a perfect 100% clone of GPT-4.
No, of course not.
It's just mathematically impossible to align them perfectly on every conceivable topic in the universe. So what happens when the proxy is faced with a weird, highly specific prompt, completely misunderstands the teacher's logic, and hallucinates a confident but totally wrong probability distribution?
That's a very real problem.
Doesn't the student just absorb all that garbage, soft-label data?
That is the exact vulnerability the researchers anticipated. And it is why they introduce a brilliant fail-safe during the final 45% of the data.
Which is what?
That's the actual distillation phase, where the student is finally learning from the proxy. They implement a mechanism called sample level weights.
Sample level weights. Okay, so if the system needs to grade the proxy's homework on a question-by-question basis, wait, how does it know the proxy is wrong?
Think about it.
If the system can't see the black box teacher's internal math, how does it know the proxy's internal math is hallucinating?
Exactly the right question.
Oh, is it reverse engineering it? Like, is it looking at the proxy's internal probability distribution to see if that specific math would naturally arrive at the teacher's final word?
You've hit the nail on the head.
Yes.
During this final phase, the system evaluates the proxy in real time. For every single training prompt, it looks at the proxy's internal probability distribution and asks a very specific mathematical question.
Which is?
If the student were to perfectly learn this probability distribution, how likely is it that the student would ultimately generate the exact hard label words the black box teacher actually said?
That is incredibly clever. It's basically checking the proxy's scratch pad against the teacher's final answer to see if the math checks out.
Exactly. When the math checks out, meaning the proxy's internal logic highly predicts the teacher's actual words, the system assigns a very high weight to that training example.
Okay.
It signals to the student model, pay close attention to these sock labels. The proxy scratchpad is perfectly aligned with the genius model here.
And if it doesn't check out?
If the proxy goes off the rails, if its internal probability distribution makes it mathematically unlikely to arrive at the teacher's actual answer, the system assigns a very low weight.
So it effectively tells the student, ignore the substitute teacher's scratch pad for this one. They are babbling. Just memorize the genius professor's final hard label answer.
Right. It seamlessly and dynamically blends white box and black box knowledge distillation on a sample-by-sample basis.
That is so smart.
It protects the student from the proxy's inevitable hallucinations while squeezing every single drop of useful, transparent logic out of the proxy's successes. And when they removed this weighting system in their ablation studies, the students' performance degraded across the board.
Proving it works.
Proving that filtering out the proxy's bad days is absolutely essential for the student's success.
Okay. Mathematically, protecting the student from the proxy's hallucinations makes perfect sense. But, theoretical failsafes don't always survive real-world testing. Did this architecture actually solve the performance gap when they put it in front of complex reasoning tasks? Like, how does it actually perform out in the wild compared to the old compromised methods?
The results represent a massive leap forward for small models. They ran the resulting 7 billion parameter student models through a gauntlet of standard AI benchmarks.
Like which ones?
AG-EVIL for general knowledge, ARC for science questions, CSQA for common sense reasoning, and the really notoriously tough ones, BBH for complex reasoning, and GSM8K for mathematical reasoning.
Give me the numbers on those math and reasoning benchmarks, because that's usually where small models completely fall apart.
Right. So to give you context, GSM8K is a data set of grade school math word problems.
Okay.
Things like, if Jane has 5 apples and eats 2 every Tuesday, how many does she have in a month? The model has to actually show its multi-step work to get it right.
Sounds simple, but it's hard for them.
Very hard. Using the tiny, highly efficient Llama 27B model as the student, traditional black box KD, where just blindly copy the teacher's answers, got a score of 49.51. But when trained through the new Proxy-KD method, that same tiny student hit a score of 53.07.
Wow, that is a significant jump for a model that small on a math benchmark.
It's even more pronounced on BBH, the complex reasoning dataset. Traditional methods scored a 46.68. Proxy-KD pushed the tiny student to an impressive 53.4.
Jeez.
What's incredible here is that this tiny Llama 27B student is vastly outperforming much larger models that were trained the old way.
And what about the physical size of the proxy itself? Did they test if that mattered?
They did, yeah.
Because, if a researcher has to rent massive cloud GPUs to run a 70 billion parameter model just to train their 7 billion parameter model, that's still a pretty heavy logistical lift.
They absolutely tested that variable, and proxy size is a major factor. They ran a parallel experiment using a much smaller Llama 213B model as the proxy instead of the 70B version.
And what happened?
The students' final benchmark results were noticeably worse across the board. The fundamental takeaway is that a larger proxy has a much greater inherent capacity.
More neural pathways, that sort of thing.
Exactly. More complex parameters to align with the massive black box teacher. The 13B model simply couldn't bend its smaller architecture enough to successfully mimic GPT-4, whereas the 70B model had the raw architectural flexibility to actually capture and translate that genius logic.
It reminds me of a method I read about a few years ago in computer vision literature called TAC-ED, Teacher Assistant Knowledge Distillation.
Yes, TAC-ED.
It sounds structurally kind of similar, using a middleman. Did the researchers look into how Proxy-KD compares to that older method?
They made it a point to run that comparison, and it highlights exactly why Proxy-KD is so innovative. TAC-ED also uses a middleman network to bridge the capacity gap between a big teacher and a small student.
Right.
But here is the critical point of failure. TAC-ED was built years ago for purely white box environments where everything is already visible.
I see.
Because of that, it completely lacks the DPO preference alignment phase we talked about.
Yeah.
When the researchers tried to apply the older TAC-A method to this modern black box scenario, the results were disastrous.
Yeah.
It actually performed worse than basic black box KD.
Wait, having the unaligned teacher assistant actively hurt the student compared to just copying the final answers?
Considerably.
Yeah.
For example, on the Llama 17B student, basic black box distillation scored an average of 49.1 across the benchmarks. Throwing an unaligned TKD middleman into the mix dropped that average to 46.63.
Oh, wow.
Yeah, it decisively proves that just inserting a proxy into the pipeline isn't enough. If you don't aggressively align it using something like DPO to shift its probability landscape, the proxy just acts as a giant noise generator. It confuses the student with conflicting logic rather than helping it learn.
So bringing this all back down to earth, why does this matter for the listener?
Yeah, that's a good question.
Why should you care about Proxy-KD, KL divergence, and benchmark scores? I mean, it ultimately comes down to the democratization of top-tier AI.
Absolutely.
Right now, if you want complex mathematical reasoning in an application you are building, or even just for your own personal workflow, you're basically forced to pay per-token API fees to massive tech monopolies.
And your private data gets sent to their server.
Exactly. But if Proxy-KD allows the open source community to squeeze that heavy-duty reasoning into a 7 billion parameter model, it changes the entire landscape.
It really does.
It means the possibility of running a highly capable, reasoning-heavy AI locally on your own hardware, totally private, customized to your exact needs, without paying a dime in server fees. It is a massive step toward breaking the monopoly of the black box.
Looking at the bigger picture, it represents a fundamental shift in how we handle artificial knowledge.
Yes.
We are moving away from hoarding intelligence in massive centralized servers, and we're discovering the mathematical tools to efficiently distribute it anywhere.
To recap the journey we took today, we started with the massive bottleneck of closed AI models and the inherent limitations of both white box and black box learning.
Right.
We explored the clever architectural shift of introducing an open-source proxy model to act as a transparent substitute teacher. We dug into the crucial, non-negotiable step of DPO alignment that physically alters the proxy's neural pathways. So it actually things like the genius teacher.
Essential step.
And finally, we unpacked the game-changing sample-level weighted distillation that dynamically protects the tiny student from the proxy's inevitable hallucinations, leading to those massive leaps in real-world reasoning benchmarks.
And, this methodology raises a really fascinating question for the future of the field.
What's that?
If a small 7 billion parameter model can achieve this incredible level of complex reasoning just by mimicking the shadow of a giant model cast through a proxy, what happens next?
Right.
What happens when researchers start chaining multiple specialized proxies together? Or better yet, what happens when these heavily optimized tiny student models start generating their own internal, highly efficient logic that the original black box teacher never even possessed?
Oh, wow.
Are we just compressing existing knowledge, or are we on the verge of creating entirely new, highly efficient forms of artificial intuition?
That is a wild thought to leave off on. In our attempt to teach them to mimic the giants, we might be accidentally giving them the tools to start thinking for themselves in ways we never even programmed. A huge thank you to you, our listener, for joining us on this deep dive into the vault. Keep learning, keep questioning the complex world around you, and we'll see you next time.